The research discusses the entropy of rectifiable and stratified measures, focusing on the geometric measure theory. It starts with the asymptotic equipartition property, which ensures the concentration of measures on strata of a few typical dimensions. This property is used to derive the entropy chain rule for stratified measures, which generalizes discrete continuous mixtures and may have a singular continuous part. The entropy of these measures obeys a chain rule, with the conditional term being an average of the entropies of the rectifiable measures involved. The discussion also includes elements of geometric measure theory, such as the Hausdorff measure and dimension, which are essential for understanding the volume of sets that are not necessarily smooth. The research provides a detailed analysis of these concepts, connecting them to the entropy of measures and their properties, ultimately contributing to a deeper understanding of the geometric and measure theoretic aspects of information theory. In the context of geometric measure theory, this research paper explores the concept of rectifiable and stratified measures, focusing on their entropy properties. It begins by defining the Hausdorff dimension of a set A, which is determined as the unique value of M for which the Hausdorff measure him, A, transitions from infinity to zero. The paper also discusses the area and CO area formulas, which are fundamental in computing integrals over rectifiable sets. The area formula, given in proposition 2, states that for a Lipschitz function f, Rk right-pointing arrow rho with k is less than or equal to d, and a Lebesgue measurable subset E of Rk, the function y right-pointing arrow sigma x element of E intersection f caret 1 y u x on rho is Higg measurable. Furthermore, the integral of u over E can be expressed as the integral of this function over rho multiplied by the k-dimensional Jacobian Jk, f, of f. This result has implications for the computation of lengths and areas of curves and surfaces, as demonstrated in examples 1 and 2. The CO area formula, a generalization of Fubini's theorem, allows for the computation of integrals over countably m rectifiable sets as iterated integrals. This is achieved by integrating over the level sets of a Lipschitz function f. Rk right-pointing arrow rho, where d is less than or equal to k, and then integrating over t and rho. This procedure is particularly useful when E equals Rk and f is a projection onto a subspace generated by some vectors of the canonical basis of Rk. The paper also touches upon the concept of countably m rectifiable sets, which are defined as countable unions of m rectifiable sets. These sets have sigma finite measures and are crucial in the study of geometric measure theory. The paper highlights that any subset of an m-dimensional C1 submanifold, differing from it by an H-null set, is countably m rectifiable. Overall, the paper delves into the intricacies of geometric measure theory, providing insights into the properties of rectifiable and stratified measures, and their relationship with Lipschitz functions and Hausdorff measures. The area and CO area formulas presented are essential tools for researchers working in this field, allowing them to compute integrals over complex geometric objects efficiently. The paper discusses the concept of rectifiable and stratified measures, focusing on their entropy properties. It begins by presenting a CO area formula for a Lipschitz function f. Rk right-pointing arrow rho, where E is a countably m rectifiable subset of Rk with m is greater than or equal to d. This formula states that the set E intersection f caret 1 t is countably HMD, MD, rectifiable and HMD measurable, and the function t caret m asqrt d right-pointing arrow integral E intersection f caret 1 t g y dhmd y is LD measurable on rho. The CO area formula is then applied to compute the entropy of a probability measure ρ, which is absolutely continuous with respect to the restricted measure E. The paper also delves into the study of m-rectifiable measures from the viewpoint of information theory, particularly the properties of the entropy HHM ρ of an m-rectifiable probability measure ρ. A key result from Koliander et al. 2016 is summarized, stating that if A is a bounded Borel subset of Rk, f is an injective Lipschitz function on A, and ρ is a probability measure such that ρ much less than Lk, A with density R, then f rho much less than hk, f a, with density r jkf caret 1, which is well defined, hk, f a, almost surely. This leads to the formula for the entropy of rectifiable measures as hhk, f a, f rho, equals hlk, rho, plus integral, east rho, lane jkf. Moreover, the paper introduces a chain rule for the entropy of rectifiable measures as a consequence of a general theorem for disintegrations. Given a countably m rectifiable subset E of Rk, a Borel function f Rk right-pointing arrow road, with D is less than or equal to m, and a probability measure ρ such that ρ much less than E, it is shown that f ρ much less than LD, and the entropy can be expressed as HHM E rho equals HLD f rho plus integral RKHF caret 1 HMD E intersection f caret 1 T rho T df rho. This chain rule facilitates the computation of the entropy of rectifiable measures in terms of the usual differential entropy and the entropy of lower dimensional measures. In conclusion, the paper provides a comprehensive analysis of rectifiable and stratified measures, emphasizing their entropy properties and how they can be computed using various formulas. These results contribute to the understanding of the behavior of such measures in the context of information theory and differential geometry. The paper discusses the concept of stratified measures, which are a sum of rectifiable measures with different dimensions. A fundamental example is a discrete-continuous mixture, where each component has its own dimension. The product measure of a stratified measure is also stratified and can be grouped by dimension to be put in the standard form of definition 3. The main result of the paper, Theorem 1, provides a refined version of the asymptotic equipartition property, AEP, for stratified measures, giving an interpretation for the conditional term in the chain rule, 14. This theorem states that for any epsilon greater than 0, there exists an n0 such that for any n is greater than or equal to n0, the restriction of ρ to t, n, delta ρ, n, satisfies dtv, ρ circled times n, ρ, n, less than epsilon. Moreover, ρ, n, equals a sum of m rectifiable measures for m element of nay d n caret 1/2 plus xi nay d plus n caret 1/2 plus xi. The conditional entropy h x y quantifies the volume growth of most doubly typical fibers in the sense that for any y in a n delta 1 has north caret 1 lane y t n delta y is less than or equal to h x y plus delta n. The paper discusses the entropy of rectifiable and stratified measures, providing a geometric interpretation to the possibly non-integer dimension E, D. This is achieved by considering sets A, n, and B, n, with specific properties, which are used to bound the entropy of the measure m, y, from above and below. The main result shows that under suitable hypotheses, the information dimension of the measure ρ equals the limit of the logarithmic growth rate of the cardinality of B, n, as n tends to infinity. The paper also references various works in the field, including the theory of rectifiable sets and tangent measures, geometric measure theory, and the concept of information dimension. It uses mathematical tools such as Federer's geometric measure theory and Ambrosio, Fusco, and Pallara's functions of bounded variation and free discontinuity problems. The paper further explores the connection between entropy and disintegrations, a concept introduced by Vigneaux in a 2021 publication. This connection is crucial for understanding the relationship between the entropy of a measure and its disintegrations, leading to a more comprehensive understanding of the geometric properties of the measure. Moreover, the paper touches upon the concept of typicality for stratified measures, an idea explored in another work by Vigneaux in 2022. This concept is essential for understanding the behavior of measures under different stratifications, providing insights into the structure and properties of the measure. In conclusion, the paper presents a novel approach to understanding the entropy of rectifiable and stratified measures, leveraging geometric measure theory, information theory, and recent advancements in the field. It provides a detailed analysis of the relationship between entropy, disintegrations, and typicality, shedding light on the intricate properties of these measures.